So are you guys totally confident about your external exam on 9th of November? All right, so most schools will give a bit more information in term 4, but just to know that it's happening and have a heads up on that. Um, I'm doing a bit of a countdown. It's always a bit alarming. Um, this last term, there's so much to do, and it is really important that you start revising. Now, I already know that Pete is. Um, Hannah and Callum, have you started some sort of revision program? All right, a little bit. All right, welcome, Callum. So it is absolutely essential. I think one of the best things you can learn from the mid-year is that it is revision, but sometimes it's almost parts of it, it's almost like starting from scratch, and it always takes longer than you think. So there's a principle of if you think it's going to take 2 hours, it'll probably take you 4. So please do get some sort of plan, and it's a plan that can change. So you might have a plan of achieving a certain amount this week as far as revision goes, and then you've got to say, oh, well, actually, I didn't manage it. But when you don't manage it, like if you've got an overall plan, when you don't manage 1 week, it means you've got to reduce your goals. All right? So postponing no longer works. Time is definitely limited. So we've got 2 fairly small skills and application tasks. One due next Friday, September the 1st, which includes the information that comes in today's lesson. And then another one that is, so the one that we've set that's coming on continuous random variables is about 50 minutes. And the next one will be 50 minutes as well, or maybe even shorter. But as well as that, there is a folio task that I have put in Google Classroom. You're most welcome to read it and even begin thinking about it, but I'm not going to introduce it properly till next week. So we've been looking at random variables, and we have really just considered the whole population. In reality, when we're collecting data, often it's almost impossible to collect a census of the whole population. So there's various sampling techniques. Now, one idea of sampling is just to take, they call them observations, take observations and say, I'm going to use small numbers, all right? I'm going to take 3 observations and add them together. So my test statistic is adding 3 observations together. So if it was looking at the average goals for a footballer, for footballers in a certain team, you'd randomly pick 3 in the team and add the number of goals that they kick. And then you'd take another sample of another 3 and add together their goals. So the statistic is different, like it's adding the 3 outcomes together. So I just want to show you that technique here, just with the advice that it's on the way to the technique we do use, okay? So this sampling distribution, this is just pretty meaningless, okay? If we are just given an outcome xi, which is getting a 2 or a 3, so maybe it's a dice roll and we're interested only in a 2 or a 3. Find the probability distribution, and so we've called it S2, of just adding those characteristics together. So what are, if that is our new statistic, what are the outcomes that we could have? Yes, Pete?
They would be 4, 5, and 6.
Excellent. So we're adding any 2 together, and just give a tick if you agree with Pete. 2 and a 2, 2 and a 3, 3 and a 2, which is the same outcome. or 2 3s. All right, so to work out the probability, we would have to say to get a 4 is a 2 and a 2. The probability of getting a 2 is 2/3, and a second 2 is 2/3, so that's 4/9. The probability of getting a 5 is a 2 or a 3, or a 3 or a 2. So it's going to be double. Getting a 2 is 2/3. Getting a 3 is 1/3. That's 4/9 as well. And then getting a 6, you guys work it out. Can you work out the probability of the outcome being a total of 6? All right, let's see if everyone agrees. It's a 3 or a 3, no choice. Oops, I shouldn't be writing it there. 1/3 times 1/3 is 1/9. Yeah, that's good, Hannah. Do you mind next time doing it to all participants? Okay. So this sampling technique, some of the concepts is that the sample, to be fair, has to be able to take all the variations. So you started out with 2 outcomes, 2 or 3, but this sample, where the statistic is adding 2 of the outcomes together, it actually has more outcomes. If we spent time, and the textbook has a lot of explore in it if you wish, if we took time, can you see that the number of outcomes, oh wait a minute, I haven't done the mean yet. I haven't quite finished. Let's do the mean first before I go on. You might remember that when we calculated the mean, the way we did it was the sum of each outcome, we call that xi, times by its probability. So it will be, for the original population, the mean would be 2 times 2/3, which is 4/3, plus 3 times 1/3, which is 1. 4/3 plus 1 is 2 and a third. All right. Give me a tick. Do you remember that process from about 4 weeks ago? That's good. So part of this sampling is you might need to go back, and to work out the standard deviation of the original is the sum of the value we're looking at, take the mean, all squared, times the probability. All right. Now, I don't want to take too much time on this, but this is something I really want you to go back and do. So I'm just going to stick with the mean. So we worked out the mean is 2 1/3. Let's do the mean of this sample distribution. 4 times 4 is 16 on 19. You guys do it as well. See if you can. I'm just doing the mean. 520 on 9. Tell me if I make a mistake. 6 9s. Now, running equals are bad, but I'm doing it on the screen. 36, 42 on 9. Now, if we wrote that, let's write them both as a decimal. The 2 1/3 is 2.3 recurring, and 42 on 9 Ooh. Did I make a mistake? Yeah, I get that as well. 4.6 recurring, that's 4 2/3. So that's more than double. Can you see that the mean of this sampling distribution is a bit more than double the original. Just give me a tick if you can see that the mean is larger. Now, I've used such small numbers, I wanted it to be triple, okay? Now, if we did this often enough and we did it with something a bit larger, that's the pattern you would see. That if there were 3 outcomes, or 3 observations, I should say, if there were 3 observations, then the mean would actually be n times the original, 3 times. So the mean for this observation, so I'm just going to put mean 3 because there were 3 observations, would be 3 times the original mean. And so in general, mean of n observations would be n times the mean. Can you just predict, we haven't done it, can you predict what would happen to the distribution, the standard deviation? So you've got a choice of 3. Would the standard deviation of the sampling distribution, would it be the same as the original? Yeah, gets bigger or decrease. So we've got disagreement. Hannah, what basis did you think of when you say bigger, a bigger distribution? Yeah, that's right. What were you thinking there?
Well, you've got more values. I don't know, a bigger range of values, so the distribution will be different because they're bigger.
All right, thank you, Hannah. And Pete said that he guessed. Did you have any vague thought with your guess there, Pete?
I thought that because you're working with the same values, they're gonna like sort of work. Yeah, not real sure, but
Now, Pete, I'm going to propose that you're not real sure because Hannah, you're both talking about the same thing, but Hannah noticed that the sampling technique has more outcomes and therefore there's going to be a greater spread. And Pete, you almost said that. You said they'll be the same, but can you see there's not the same number? Can you see there's more?
yeah.
So you're actually both thinking right, and the conclusion is that the distribution is actually more spread in this sampling technique, this sampling of adding observations together. And when you do it lots of times with lots of different observations and sets, you'll find that the standard deviation, sorry for this very messy screen, you'll find that the standard deviation, if the red one is the original, then of the sampling, if there were 6 of them, then it will be square root of 6 times the original one. Or if it's n, if there are n observations, it will be the square root of n times the original standard deviation. All right, so it is more spread in this technique. So that's a summary of what we've said so far. So just have a quiet read. Just please, could you put a tick on the screen when you've read it? Yep. So over to you guys. I want you just to use these sampling observations. We often use 9 or 25 or 16 because the formula for working out the standard deviation for the sampling distribution is sigma square root of n. So square root of those numbers is easy to find when you're just practicing a skill. Yeah, that's it, Pete. All right, so I see Pete and Hannah have put information up. Callum and Reese, are you confident? Can you do that tiny little calculation? Yep, that's good. No. Exam writers aren't practicing skills. By the time you get to the exams, everyone, the focus is not on simple skills. The focus is on applying those skills. So that's right. Exam writers are not helpful in that way. All right. Now, that's one sampling method. And what I'd like you to do, can you get access to the SACE board formula sheet? I emailed it out to everyone only 15 minutes ago. I can, yeah, so please just give me a tick when you can see it. Those formulas are not on the formula SACE board sheet. So if you have a look, you might see discrete random variables, and yes, calculating the mean that we just did, the sum of the individual outcomes times the individual probabilities, that's there. The standard deviation that I didn't bother to do, which is the square root of the sum, I didn't write it down correctly on the screen, I noticed. I left out the square root. All right, so that's there, but the formula that we've just done is not on this sheet. Now, perhaps that's because this sampling distribution is something that we look at as a step towards understanding the next bit. But when you do your weekly work, I want you to use this formula sheet so that any formula that's not on there, that's what goes onto your single page of handwritten notes. And it's very important. What you'll also find is sometimes the way they write it on the formula sheet, it's not necessarily the way you use the formula. Not very often, but sometimes you might wish to write it in a different format on your own handwritten sheet. Right, so now we're going to move on. As you've noticed, this sampling mean is larger than the original mean. If we had n observations and we took the average of all those observations, so we divided, so our sampling distribution is to add all the observations together. If we then divided it by the number, that gets another mean. But this number is a statistic. So even though it's the mean of observations, when we plot those observations, our statistic is now a mean statistic, but we take a whole variety of these sampling observations. So we do it like if we're using 9, we take 9 observations, add them together, take their mean. That is a statistic that we can plot. Then we do it again. We take another 9, add the observations together and divide it by the number 9. That's another statistic that we can plot. Now these statistics, which are means in their own right, we can plot. Now there's a lovely little software that just shows you this gradually building up, this random, and how when there's enough of them, it approximates a normal distribution. So if the original population was normal, then this sampling method will also definitely have a normal distribution. Now, when we divide by n, so the test statistic now is the mean of the observations. I just want to quietly work through. We worked out the mean by finding the expected value. So that's another way of expressing the mean. We found the expected value by summing up the individual observation times the individual probabilities. And now we're dividing by n. So we've found out that this expected value mean is n times the mean. Now we're dividing by n. What we get back to is the original mean. Do you follow that? That the mean of this sample statistic, which is means, actually is the same as the population mean. Do you follow that reasoning? That little bit of maths? Oh, yeah. Is that a joke, Pete? All right. That is one of the problems with this. Okay. You've really got to have fixed in your head what mean we're talking about. All right. So that's nice. That's nice that we can have a sample test statistic whose mean is identical to the population. All right. Now, if we do the same process with the standard deviation. All right, so we're taking the average, I might use that word, taking the average, so the standard deviation of the sampling distribution, here it is, standard deviation of the sampling distribution, you've only just learnt that, it was the square root of n times the standard deviation. Now we're dividing it by n. So let's just rearrange that. We've got 1 over root n divided by n. Now, if we didn't want a root n on the numerator, we could multiply it by the number 1. All right, root n on root n is 1. We haven't changed it. Give me a tick. Do you follow that? Because we use this a lot. Okay, so root n times root n is n. So we get the standard deviation times n on n root n. And n is the number of samples. So it is going to be a positive number. So we can cancel n. It's not going to be 0. So now we've got it in the form here. All right, this is the way that we do samples. All right, and what is the consequence of having the standard deviation divided by the square root of n where n is greater than 0? What is that going to do to the standard deviation? Any ideas? Yes, it is an inverse proportion. Can you add to that visually? What's it going to look like? It will. Now, Pete, you're doing a fantastic job there. Everybody, whenever you're tempted to write it or think it, could you replace that with standard deviation? Whatever you're talking about, it's a good learning technique to name what you're considering. It's a little bit stilted, but it really helps you the clarity of your thinking. So the standard deviation will get smaller. So here we go. We've got an original population, and if we plot a whole heap of, I'm not quite sure what to call them, sampling means, if we plot a whole heap of sampling means, and the sample size is quite small, like 9, that would represent this first one. If we increase the sampling size to, say, 25, it'd be standard deviation over the root of 25, which is divided by 5. It will be 5 times narrower. And then if we go up to n equals 36, square root of 36 is 6, be the standard deviation divided by 6. Now, I just want to mention, I've gone from 25, so I started off with 9, so standard deviation on 3. I didn't do 16, but if you just listen to those sample sizes, 9, 16, 25, 36, 49, oops, 36, 49. To get, because it's the square root of the number, to get a narrower distribution, which is often what we want, you need to get a much larger sample. So, you know, that's expensive. So in actual fact, we go for the smallest viable sample. Now, there's one other concept that I'll just mention now while I'm at it. In real life, when you're sampling, if you want a fair random sample, you've got to do replacement. So when you take that sampling distribution of observations, then you can use the same observation data over and over again. So if you go to the footballers with their number of goals, you can count the same person in the next sampling distribution. Now, in reality, we generally don't. We generally get a sample, count it up, get a sample that is different. Now, if it's a huge population compared to the sample that we're using, it doesn't skew the results. But in general, the sample size that you take compared to the population has to be small. The tension is the sample size also has to be large enough to give us a reasonable result. All right, so that's just some background information. And there is later on, if you go on and do more statistics, there are formulas that will generate what is a viable, reliable sample size. A very simple one is if the probability of success n times the probability of failure p, if the probability of success n times by the population size, I don't have a letter for the population size, times by the population size is greater than 10, or the probability of failure times the population size is greater than 10. If both those things are greater than 10, usually the sample distribution will represent the population. So that's pretty small. Okay, just a little bit of practice at using these formulas. So these formulas are the ones that you tend to use the most, all right? The mean of the sampling distribution means is the same as the population. That's nice. The standard deviation of the sampling means is the standard deviation of the population divided by root n, which is the number of samples or the number of observations. So over to you guys. Can you just do 6 part A? When you're doing it on paper, please make sure that you use the correct symbols and you think about them, all right? So yes, the mean. Don't get distracted by Peter because I think Peter's made a mistake. Peter, you might have a little think about what you're doing, all right? Because this is where we take the sampling observations and we average them. And so the mean is the same as the population mean. Just write it down, 20. But the standard deviation of the characteristic, which is the mean of 25 observations, that is going to be the standard deviation of the population 2 divided by the square root of 25, which is 5. And you'll notice that the standard deviation is narrower than the original. Oh, I've done part B. Pete's right, I'm wrong. Pete's done part A, I've done part B. Okay. I didn't read the question, did I? All right. Can everyone see? Pete is right for part A, and I've gone and done part B. Give me a tick if you follow those two answers there. I'll give you some thinking time. When you look at your formula sheet, please take note that these formulas are not on the formula sheet. And so again, it's something that you might want to add to your handwritten notes, that you can take 1 page of handwritten notes for each of the separate tests, and for the external exam you'll have to condense them, and it'll be 2 pages, which is 4 sides of handwritten notes. All right, so if we've understood what we've been saying, you should now be able to answer question 7. Can you just highlight the key bits of information for question 7? All right, so one of those histograms is the population distribution, and one of those histograms is the mean of the sample observations, that distribution. So let's just start with which is the population histogram. Everyone make a decision, A or B. Let's see what your choices are. All right, Reese, I haven't heard you talk too much. So Reese, why did you choose B? Ah, okay. The yellow arrow person, who was that? Pete, do you want to explain your choice?
We're given that it's a random variable x, and we know we're not dealing with those in the normal distribution, so I looked at B and saw that it wasn't normally distributed.
Thank you. All right, so any got responses, any other reasons that people chose B? Yes, Hannah?
I chose B because it was lower, and I don't know if it's wrong, but the standard deviations are fatter.
Yeah, wider, yes. All right, so both those reasons are valid reasons. Both Pete's reason and Hannah's reasons add together to make us feel sure that histogram B is representing the population. And if we have sufficient samples of 20 observations that we average, we know that the standard deviation will get narrower. Now, if we have a quick look, it's actually easier on histogram A. The mean, I don't know what it is exactly. It looks like it might be 24. So as a guess, I'm guessing that the mean is 24 on the sampling means. And 24, because this is skewed right, do you agree that the data tails off to the right? So it's skewed right. So there's more data to the right. Yeah, it's a bit hard, but it looks like it's in the block 20 to 25. So the means do look the same. All right. And we've commented on the shape. Now, the shape should be that the total data, so if I do an approximate function to represent the distribution, the area represents the total probability of 1. The area needs to be the same. So the fact that the sampling distribution histogram is higher, so the data in the middle occurs more frequently, the data is higher, it means that the area of them are the same. Can I have a tick if you realise that if your distribution is narrower, then the frequency in the middle has to be higher so that the total area in the comparison is the same. Yeah, that's good. Now, it's identical when we have the standardized distribution. So when we standardize everything and then it is a fair way to compare. It's a bit tricky to compare when the standard deviations are different sizes. So that's why we go to the z-scores. So, that's quite handy because that's what we want to do next. So, you may recall that the z-score of the population is simply the characteristic value of a single value, take away the mean of the population divided by the standard deviation of the population. Now, if we want a z-score, for instance, of samplings of 20 observations, then instead of, so we'll have the value x still, the value x will be a mean of 20, and we'll take away, who can tell me, can you text chat, what is the mean of the averaging sampling observations? The mean is not nasty, it's the same, okay? So it's the same as the population, which I hope what Pete's saying. So the mu stays there. What is the standard deviation of the samples? It's a bit hard for you to type it, so I will just tell you. It is the standard deviation divided by the square root. Well, in this case, it will be 20, all right? So if instead of saying 20, I said n, the z-score for n, so the characteristic we're after is the means, and there's n of them. So it will be x bar n, take the population mean because it's the same as the sample means, divided by the population standard deviation root n. So everything you did with z-scores before, you can do with z-scores for the sample. You just have to modify the formula. Now let's go back to the formula sheet and look for z-score. Again, it's not there, all right? These are all very simple formulas which, when you're using them, they're very easy to remember. But when you jumble every topic you've learnt during the year, sometimes under pressure, some of these very simple formulas, oh, it is there. Sorry, I can see it bottom right. Tick, can you see capital Z equals capital X minus mu over standard deviation? So capital Z is the characteristic z-score. All right, so it is there, but the sample z-score is not, okay? So it's really useful to do what I've just done. Look for it, know where it is on the page. So again, when you're under a bit of pressure, you know where that formula is. You can look straight to the right spot without thinking like I did, oh, it's not there. Now, I've actually quickly covered the concepts from A, B, and not C. So the last concept that I want to discuss is if you're making a statistic from the sample distribution means and the original population is normal, then the sample distribution means will be normal. What is really very useful is if we have a data set that is not quite normally distributed. So this is representing a population data set. It's skewed which way? Can you text chat? What direction is the skew of that data? And remember, the skew is towards the tail, the side that tails off. Okay, Hannah, we're learning German as well as maths. That's great. Okay, So off to the right. So it's skewed right. It's not a bad severe skew, but it's not a normal distribution. Now, if we took observations, added them together, divided them by the number of observations, so we've got an average or a mean, and we plotted that distribution, if we have sufficient samples, I'm going to go to the white, pity I haven't got a picture. I want you on the whiteboard, just grab a spot please, 4 of you. I'll make 6 spots. Now, I want you to draw your own skew. So you're going to do 2 diagrams in your little square. Oops. I want you to do a tiny diagram that is the population with a skew. And then I want you to, so that's population. Now, if you take a sample distribution and you take enough of them, you will get a normal distribution. So now I want you to do the sample distribution that is normal, but I want you to think about where the mean is. So to help you, I want you to think about where the mean is, and my mean on that one's a bit off. I'll try again. So I want you to draw a comparative graph. It's great that we can learn from each other, and looking at Callum's graph, having a comparative graph one under the other with the same scale is an excellent way to be able to easily see. And Hannah has also emphasised she's got the mean exactly the same spot. Perhaps a vertical axis would also be helpful, but that's very good. All right, and so as we compare each other's graphs, everyone has shown that the distribution of the sample means is narrower. So the standard deviation is narrower. And because it's narrower, and that the mean corresponds, same mean as the population, and to get the area equivalent, it needs to be higher. Now, when it's much narrower, it's got to be stacks higher, and you'll find that most of the sketches do not represent that. So if I did a very narrow distribution compared to my population, I would need to go much, much higher. And if you had nice graph paper and you're doing a nice plot, Pete's got actually many of you have got a very nice shape, but if I look at Callum's, his inflection is approximately here. So what I'd like you to do is pick or make out where your inflection is and label where one standard deviation occurs. So if on mine I make out my inflection is there, then it will be to the left of the mean. It will be, there's not enough room. The mean take 1 standard deviation. And the last thing before we end the lesson is that 99% of the data is within 3 standard deviations left and right. So that's a total of 6 standard deviations. So if you look at your sketch, and I'll keep on using Callum's, Callum has perhaps, if I look to the right and scribble on the right, if that is the mean and that's the mean plus 1 standard deviation, then we actually want equally spaced the mean plus 2 standard deviations, 1, 2, 3, so 3 standard deviations. It should taper a little bit slower. just a little bit slower. All right, so that it's got the 3 standard deviations left and right. Smiley face if you can see that even though it's a sketch, there's a lot of things to try and show accurately. All right, now give me a tick if you saw the modified weekly work that includes A, B and C, not just A, because next Friday, September the 1st, that work, including C, A, B and C, will be in the test. All right, so make sure that you get totally up to date. Now, the topic just smoothly continues, so I will continue. I'll probably recap a little bit next week on part C, which is the central limit theorem. I haven't talked a huge amount about that today. So central limit theorem and on into confidence intervals, which will be the next topic. I'll just mention again that we will also begin a folio task, which is looking at functions. It's looking at surge and logistic functions, which at the very start of the year we looked at, but we haven't really done much with them since. Any questions before the lesson ends? All right, everyone, have a very good week. See you, everyone.